So now we're going to talk about something that is kind of a specific part of big data. So the velocity part, huge amounts of data being generated all the time, which essentially is a data stream. So that's a flow of instances. So you could have a flow of images coming in, have a flow of video coming in, or just a flow of essentially lines to go into a database. The thing about the dynamic data is that the patterns within it can change. So if we've got, for example, a static machine learning model, that's not going to deal very well with a changing pattern happening in the data. We build a single model at the start, we use it to make predictions on later data. The model accuracy can kind of degenerate over time as that data changes. The problem of kind of designing algorithms to deal with this real-time data has been a research topic for kind of several years now. There's several real-world applications on top of that as well. So if you think about banks trying to detect fraud, as patterns change of different frauds occurring, they want their models to kind of be able to update all the time. Similar for intrusion detection systems in computer networks, they want to be able to update and keep on top of what is happening. Ideally, we would want this to happen automatically, so minimum interference from humans, because otherwise they've got to spot when changes are happening. We just want the machines to be able to do it by themselves. So if you think about a traditional classification problem on a static batch of data, you assume you have all of that data there already, you have your training test set, and you have instances with features which are x, and then there's some unknown function f of x, which gives you the class label. And you want to find a hypothesis that gives you the best prediction possible. So it kind of approximates this function as well as possible. So you have a red class and a green class, and we have instances that look like this. Our function f of x may create a class boundary that looks like this. So anything on this side is red, anything on this side is green. Our model doesn't know that, but we use standard machine learning techniques, decision trees, neural networks, whatever you want. And it learns a boundary that looks like that. And so that will do okay on whatever data set we have. It's not perfect, but it may get the results that we want. This is static classification, so we already have all our data. So we've got our data, we've done our machine learning, this is the decision boundary that we've learnt, the dotted line is what is actually the boundary. So this gives okay results. Let's now say that this is happening in a data stream. So we get this data originally, and we build this model, but then later on, we have a similar distribution of instants arriving. However, what now happens is that some of these instances are now in reality in a different class. So the true boundary is now here, but we still have our model with this decision boundary. And so we're now predicting instances here and here into the wrong class if we use that exact same model. So what we would see in this case in percentage accuracy over time, you would see at this change point, accuracy would plummet. So this problem here is called real concept drift. What has effectively happened here is that this function, the unknown function, has changed, but we've kept our hypothesis, our machine learning model, exactly the same. And so it starts to perform badly. We can also have a similar problem called virtual drift. And what would happen in this case is that the target decision boundary has stayed the same from this original, but the instances we now see in the stream are somewhere else in the feature space. Let's say we now see data like this. So although the kind of optimal decision boundary is in exactly the same place, we now have different data. That means that our predicted boundary is going to give this instance as wrong, because we haven't got a way of incorporating information from this instance into the original model that we built. Both of these will create this decrease in accuracy. So we can also look at the drift in the data streams in terms of the speed that they happen. So something that would give us an accuracy plot that looks like this is called sudden drift. We go straight from one concept in the data stream, so one decision boundary, straight to another one. Another possible thing that could happen is that our accuracy looks like this. So rather than this sudden switch, this decision boundary gradually shifts. Say in real life, if we're looking at a very, very oversimplified intrusion detection system, we have only two features that we're looking at. In the original data set, anything with these features, this is a security problem, an intrusion. Anything on this side is good. In this case, what happens is that suddenly there's a new way of attacking the network. And so suddenly what was here is now not good. So we see those patterns and we say, okay, no, that counts as an intrusion. In this case, what it means is that we see something that we've not seen before. So the model hasn't been trained with any similar data, and so it could get it right, it could fall somewhere up here, and we correctly say, this is bad. But it could also fall in an area that we didn't learn the decision boundary so well. So yeah, we get that prediction wrong. We just looked at what the problems are with using a single static model when we're dealing with incoming data. Over time, the distribution changes, and we start to see a decrease in accuracy on whatever model we built. So what happens in kind of a stream machine learning algorithm would be, so first of all, you've got X arriving. This is your instance. In our previous example, this would just have 2 values associated with it. What would first happen is we make a prediction. So in the classification example, we classify this. Yes, it's an intrusion. No, it's not an intrusion, using the current model that we have. Then what happens is we update whatever model we have using information from X. And we'll talk about some of the ways that this is done in a second. One of the kind of caveats with stream machine learning is that you need, for this to happen, you need to have the real class label if you're doing classification. So in order to incorporate information from this instance into whatever model you've got, you need to have that label there. Now, in some cases, it's very easy to say, we've seen this data, this is what it's classified as, and we can do that immediately. If we're thinking about making weather predictions, we can almost immediately say, yes, this is what the weather is like. It may be a day's delay, but yeah, that's a pretty immediate thing. For things, for example, fraud detection, you may see a pattern of data. You may predict it as not being fraud. And then suddenly 2 days later, this person figures out that actually there's something wrong with their bank account. They phone up and it does turn out to be fraud. And so we'd only have the label for that data after that has happened. The final bit is to update the model at this point. And so the goal of updating the model over time is so that rather than having a performance plot that looks like this, so we go from 95% accuracy down to 20% accuracy, we instead end up with something that, okay, we may drift a little bit here and have a tiny performance decrease, but the model should very quickly recover back to the original level, and we still have a high performance. So that's the goal of this model update. There's various approaches we can take. So the first one is explicit drift handling, which means that we first of all detect when a drift happens in the data stream. So to do that, we have drift detection methods, and these are usually statistical tests that look at some aspect of the data arriving. So if the distribution of the data we see arriving and the distribution of the classes we see is changing, it will flag that as a drift. Some of these will also look at the performance accuracy of the classifier. So if the classifier performance suddenly drops, we can say, well, we've probably got a drift here, we need to do something to the model to mitigate this.
Who spots that though? Is there an algorithm that actually spots that something's different to what it should be?
Yes, so there are various statistical tests that will do this, that will kind of just measure things like the mean of the data arriving and be able to spot things that have changed, basically. So yeah, once we've detected that a drift has happened, we then want to take some action. The first thing that we could do is we could do a complete replacement of the model. So we get rid of whatever model we had before. We take a chunk of recent data and we retrain the model on that and continue using that for predictions until we hit another drift. This is okay, but it means that we could be getting rid of some information in the previous model that is maybe still going to be useful in the future. So then there are also methods that will look at specific parts of the model and say, okay, this specific part of it is causing a performance decrease, so let's get rid of this. We can then learn from new instances something to replace this that will do it better, basically. So if you think of a decision tree, if you can detect that there are certain branches in that decision tree that are no longer making good predictions, you can get rid of them and regrow the tree to perform better.
Prune it.
Yeah, exactly. It is called pruning. You prune the branches off the tree that are no longer performing as you want them to. The alternative to explicit drift handling is to do implicit drift handling. So rather than looking at the data or looking at the performance and saying something has changed, we need to take action, we're just continually taking action. There are various approaches to implicit drift handling. So the first and probably most simple one is to use a sliding window. So if we imagine we have the data stream with instances arriving like this, we could say we have a sliding window of 3 instances. and we learn a model off of them. We then take the next 3, learn a model off of them. So as each instance arrives, we get rid of the oldest instance. And this makes the assumption that the oldest instances are the least relevant. This is usually the case. It's kind of a valid assumption to make. So this performs okay. The problem with this, though, is that it kind of provides a crisp cutoff point. Every instance within this window is treated with exactly the same kind of impact on the classifier. They're all weighted the same. So we can introduce instance weighting so that older instances will have a lower weight, their impact on the classifier will be less. So again, the more recent instances will have the largest impact on the current model. And then again, these algorithms that will use instance weighting will usually have some threshold. So once the weight gets below a certain point, they say, that's the instance gone, we delete it.
Presumably the windows can be larger or smaller.
Yes, so setting the window size is a pretty important parameter. If you have a window that is too large, then okay, you're getting a lot of data to construct your model from, which is good in the sense of machine learning, more data, usually good. But what it also means is that if there's very short-term drifts, so this drift happens and then we don't learn from that drift, if that makes sense, because we see that all as one chunk of the data. Again, if you then set the window to be too small, we can react very well to very short-term drifts in the stream, but you then have a very limited amount of data to work on to construct the model. So there are methods that will automatically adjust the window size. So during times of drift, the window size will get smaller. So we want to be very rapidly changing the model. And then during times when everything's kind of fairly stable, the window will grow to be as large as possible so that we can use as much data to construct this model as possible. So the problem with sliding windows and instance weighting is that you need all of those instances available to construct the model continuously. So every time you add a new instance and delete another one, you need to reconstruct that model. So the way we can get around this is by using single pass algorithms. So we see each instance once, use it to update the model, and then get rid of that instance. It's probably still in long-term permanent storage, but in terms of what is being accessed to construct this algorithm, it's gone now.
In that respect, then, you've got information out of the instance, but you don't need the instance itself.
Yeah, exactly. So we see the instance, we incorporate what we can from it into the current model, we get rid of it, and that instance's impact is still in the model. An example would be a decision tree. So decision trees are kind of constructed by splitting nodes where we're going to get a lot of information gain from making a split on a certain attribute. So as the data stream changes, the information gain that we may get on some of these nodes may change. So if we say get a new instance and it will say, okay, now this actually makes this a split worth making, we can make that split, continue growing the tree. And then that instance can go, we don't need it anymore, but we still have the information from it in our model. So we've got our implicit and explicit drift handling approaches. You can also have hybrid approaches. So the explicit drift handling is very good at spotting sudden drift. So anytime there's a sudden change, there'll be a sudden drop in performance. That's very easy to pick up on with a simple statistical test. But when we then add in the implicit drift handling on top of that, it means that we can also deal very well with gradual drift. So gradual drift is a bit more difficult to identify, simply because if you look at the previous instance, or like say the 10 previous instances, with a gradual drift you're not going to see a significant change. So it's a lot harder to detect. By combining the implicit and explicit drift handling methods, we end up with a performance plot that would look something like this. We maintain pretty good performance for the entire duration of the data that's arriving. The problems of a changing data distribution are not the only problems with streams. So if you can imagine a very high volume stream and high speed, we've got a lot of data arriving in a very short amount of time. If you take a single instance of that data stream and it takes you like 5 seconds to process it, but in that 5 seconds you've had 10 more instances arrive, you're going to get a backlog of instances very, very quickly. So you need to be, the model update stage needs to be very quick to avoid getting any backlog. And the second problem is that with these algorithms, we're not going to have the entire history of the stream available to create the current model. So the models need to be, for example, the single pass algorithms that can say, we don't need the historical data, we have the information we need from it, but we don't need to access these. Because otherwise you just end up with huge data sets having to be used to create these models all the time. And again, these streams are potentially infinite. We don't know when they're going to end. we don't know how much data they're going to end up containing. Most of the kind of traditional and well-known machine learning algorithms have been adapted in various ways to be suitable for streams. So they now include update mechanisms, so they're more dynamic methods. So this includes like decision trees, neural networks, k-nearest neighbours. There's also clustering algorithms have also been adapted. So basically any classic algorithm you can think of, there's multiple streaming versions of it now. So if you are interested in the streaming algorithms, there's a few bits of software that you could look at. For example, there's the MOA suite of algorithms, which interfaces with the Weka data mining toolkit. This is free to download and use, and includes implementations of a lot of popular streaming algorithms. It also includes ways to synthesize data streams, so generate essentially a stream of data that you can then run the algorithms on. And you can control the amount of drift that you get, how sudden it is, and things like that. So that's quite good to play around with to see the effects that different kinds of drift can have on accuracy. In terms of big data streams specifically, there's software such as the Spark streaming module for Apache Spark, or there's also the more recent Apache Flink that are designed to process very high volume data streams very quickly.
You just mentioned some of the software people can download and have a play with, but I mean, in the real world, as an industry and websites and things services that we use every day, who's using these streaming algorithms?
So a lot of the big companies, or most companies to be honest, will be generating data constantly that they want to model. So for example, Amazon recommendations, or like what to watch next, what to buy next. They'll want to understand changing patterns so that they can keep updating whatever model they have to get the best recommendations. Again, kind of optimizing ads to suggest based on whatever searching history you have. That's another thing that is being done via this. So yeah, there are a lot of real world applications for this stuff.
Now I've got the token, so I can load a value in, add the value from my register into it, and store it back and hand the token. And now I've got the token again, I can load something into my register.
So do the computation split across those machines. So rather than having one computer going through, I don't know, 1 billion database records, you can have each computer going through 1,000.